Okay, so let's dive back in. We're going to now start with a slightly more complicated molecule called butane. And we will look at it again through this molecules app. Butane. Okay. So there are 4 carbons in butane. That's why it's called butane. We're going to be looking down the bond between carbons 2 and 3. If we look down the bond between 1 and 2, it's kind of like ethane, only there's a methyl group on the back carbon instead of just all hydrogens. But all the conformations around this bond are the same. We can spin that methyl group around. You would predict that the barrier to rotate around would probably be a little bit higher here because you have one eclipsed interaction between a carbon-hydrogen bond and a carbon-carbon bond. Methyl groups are higher, or carbons are bigger than hydrogens, so the barrier to this rotation is probably more than 3 kilocalories per mole. In any case, though, what we really want to talk about is the rotation around the bond between carbon 2 and carbon 3. And you can see as we look down that bond between carbon 2 and carbon 3, that the carbon-carbon bond in the front is anti to the carbon-carbon bond in the back. The methyl groups are anti to each other, right? And this is the most stable staggered conformation of this molecule. It keeps the 2 biggest things on carbons 2 and 3 respectively farthest apart. So we can see, if we look at this from the side, we can tell they're anti to each other. If we look down the carbon-carbon bond, we can tell they're anti to each other. And that keeps the electron density associated with this with this methyl group here as far away from the electron density associated with this methyl group there.
So you only look at like projections for ones that are connected.
So you only look on. You wouldn't, yeah. When we're thinking about conformations, we wouldn't like skip a carbon and try to do that. We look down bonds. We look down bonds between carbons that are bonded to each other. Yeah. Okay. Well, anyway. All right. So let's imagine, or let's see whether we can rotate around this bond between carbons 2 and 3. So I'm going to try to grab the methyl group in the front and just spin it around. And you can see here we've settled in on another staggered conformation. In this case, the methyl group in the front is now gauche to the methyl group in the back. And I'm sorry that they shouldn't fade the going back into the distance quite so much. I wonder if I can. Yeah, I wonder if there's a setting I should change, but I can't see it. So, all right. So those 2 methyl groups are gauche to each other. Now that gauche conformation experiences steric hindrance, and you can see the electron density from those 2 methyl groups is close to each other. If we look at space filling, that becomes easier to see. Do you see? So carbons 2 and 3 are there in the back. Carbon 1, the methyl group here. Well, let's see, I'll point with the laser. Carbon 1 here is the methyl group 1, and then this is methyl group 4. And you can see their carbon-hydrogen bonds are basically bumping into each other. So that's steric hindrance, and that's not a problem when we're in the different, more stable anti-conformation. Now, when you have 2 non-hydrogen things, you can call this the anti-conformation, and everybody knows what you're talking about because there's only 2 non-hydrogen things. Yeah?
Just a real quick question going back to that other conformation we have.
Yeah.
So why do we see naturally occurring rings like cyclopentane or cyclohexane
really is not favorable at all.
So why do we see?
Behind each other.
Yeah, why do we see why do we see rings which to some extent require groups to be gauche to each other? And the answer is there is what we will call, well, steric hindrance, but another way of saying that is strain. And there is strain associated with forming a ring. And so, and you can, organic chemists have sort of geeked out on this for decades about actually measuring what that strain energy is. But yes, connecting a ring does have some strain associated with it. So yeah, this is the gauche conformation. This is the anti-conformation. Whoops, we swung around and went to the other gauche conformation. There's still, whoa, nope, yes, nope. Just tip it over that barrier. You see there's still a barrier. There's, I can't get away from the gauche conformation. What you're seeing is the gauche conformation is still an energy minimum, right? But it's not as low in energy as the anti-conformation. So I have to provide enough kinetic energy to get over that, that barrier whilst not getting over the next barrier. Oh, there we go. There we go. All right. And so in that anti-conformation, those two methyl groups are opposite. Notice that each of these bonds is favored to be in a staggered orientation relative to the other carbons. But methyl group here in the front, anti to the methyl group in the back. All right. So any questions you want to ask about that? Go ahead.
So the gauche is less variable, but can't get back the energy wall has to get over.
Right. So the equilibrium between staggered between anti and gauche conformations here is an eclipsed conformation, and it's hard to get over that barrier. Yeah.
Does that also mean? How do I want to phrase this? So that means that our energy minima are different, and our energy maxima also get higher.
Yes. So does that mean our energy minima are different from each other? Yes. This energy minimum for the anti-conformation is lower than the energy minimum for the gauche conformation. And barriers between them will also be different. An eclipsed carbon-carbon bond with a carbon-hydrogen bond is worse than an eclipsed hydrogen-hydrogen type of interaction. Similarly, you might expect an eclipsed interaction between methyl groups to be particularly bad. So we're going to talk about this in the same way that we did previously using Newman projections. The other thing we can do is come over here to Spartan, and because it will allow us to do conformation stuff for butane. All right, here is that anti-conformation. And then about 3.5 kilocalories per mole higher is the gauche conformation. Anti-gauche. Both of those are, come on, I pushed, yeah, both of those are energy minima, but one is lower than the other. Okay, so let's draw that in terms of a Newman projection. We'll start out with the anti-conformation. Okay, and just to remind you, we are looking down the bond between carbons 2 and 3. All right, we've got purple methyl group in the front and, oops, still same color, blue methyl group in the back. All right, so here the dihedral angle between methyl group in the front and methyl group in the back is 180. we can call this an anti-conformation. Now, let's imagine rotating the carbon in the back by 120 degrees. And let's show what that new conformation would be. The carbon in the front is going to remain unchanged, but now blue methyl group in the back is going to be gauche to purple methyl group in the front. And let's see. And, you know, we could ask, what's the equilibrium constant here between the two? We'll call this a gauche, gauche 1 conformation, because there's going to be another one. And let's just imagine their, now based on what we learned in Spartan, let's sort of draw their relative energy levels. The anti-conformation, the dihedral angle between methyl groups is 180. Then, or now, after we've rotated 120 degrees, the dihedral angle between them is like 60. And I think, actually, to do this, I'm going to need to shrink some things down. That'll work, I guess. E is for energy. All right, so the anti-conformation is most stable. We're going to put that here. That's an energy minimum. And then the gauche conformation, we've said, is about 3 kilocalories per mole higher. So I'm going to let each block here equal like a kilocalorie per mole. So the anti-conformation's there, gauche conformation's there, and this energy difference between the two is around 3.5 kilocalories per mole. Okay, and then presumably you could also continue to rotate the methyl group in the back by another 120 degrees. That would get us to another gauche conformation. Okay, and we'll call this gauche conformation 2. What should its energy level be relative to gauche conformation 1? Should be about the same, right? Dihedral angle here, we're going to say is, I guess we have to call it -60, but don't worry about the sign, right? Don't worry about the sign. We're just changing the angle to call, anyway. So yeah, we would put that energy level at about the same. And that's also, again, around 3 kilocalories, 3.5 kilocalories per mole. Okay, so equilibrium and free energy allow us to sort of discuss population of each conformation at a given temperature. So based on what you see here, which conformation should be populated more? The 181, right? And 3 kilocalories per mole, that's maybe 2 orders of magnitude in equilibrium constant in terms of difference there at room temperature. So you'd expect, and what about the populations of these two, gauche 1 versus gauche 2? Have to be equal. Whatever they are, they have to be equal. Okay, good. Now, let's deal with the transition states. The transition state between anti-conformation, which maybe we can just call A, and gauche 1 should involve an eclipsed conformation in which methyl groups are eclipsed with carbon-hydrogen bonds. So in this conformation, the methyl in the back is eclipsed with a CH in the front. The methyl in the front is eclipsed with a CH in the back. So we'll call that, I don't know, eclipsed 1 maybe. We expect that to be higher in energy than the either of the staggered conformations. And there is a number associated with that, but I forget what it is. So we're just going to sort of pretend and put it at about this level. All right, that's an eclipsed conformation, and that's a high energy transition state. As you could see from the molecules app, we don't populate that for any period of time. That's a high energy thing that we pass through on the way from one energy minimum to the other. Now, how about this barrier between Gauche 1 and Gauche 2? What would that require? I'm going to eclipse what? Okay, the methyl groups, and that's going to be somewhat hard to draw. Okay. Do you expect that to be the same energy or higher in energy than the eclipsed 1 transition state? Much higher, right, because those methyl groups have to slip past each other. So we'll go ahead and put that here, that energy level here. And your text will actually put numbers on this. I don't really care that you do that. That doesn't, you know, numbers, precise numbers aren't as important as trends. And so more stable versus less stable is fine. Okay, so then when we're thinking about rotating around bonds and thinking about energy barriers, the barrier to rotate from A to G1 is larger than the barrier to rotate from G1 back to A, right? The barrier to rotate from G1 to G2, however, is the same as the barrier to rotate from G2 to G1. Okay, let's go ahead and complete the cycle. Let's have G2 rotate another 120 degrees to bring us back to A. That will bring us back to Do. You guys don't. Sound of Music was on TV all the time when I was a kid, but my guess is that none of you even know that. Some of you? Okay. All right, good. Yeah. I don't know. I just have memories as a little kid of my dad having me sit at the piano with him, and we sang "Doe, a deer, a female deer," like again and again and again. I'm not sure how my mom how she could stand it, but that was what we did. So this is another eclipsed conformation. We'll call this, I guess, eclipsed 3. Where should I put it in energy? Is it the same or different than E2? It's different, but it should be about the same as E1, right? Same methyl groups eclipsed with hydrogens. So I'll put the line there. And then, of course, A, now we're back to minus 180, which equals 180, and so on. Oops. Okay. So, and so we could continue to repeat. Let's see, this is about 120. This would be 0. This would be minus 120. All right. So as we rotate completely around this carbon-carbon bond, there are some barriers that are lower than others. So now I want to ask you a question. To get from Gauche A, if this is my starting point, and this is where I want to end, which is going to be faster? To go here directly to Gauche 2, or to go to the anti and then from the anti to Gauche 2? So it's going to be a lot easier to go through the anti-conformation. So counterintuitively, you might think, oh, well, let's just make it simple. Going through that barrier is worse than simply rotating back through the anti-conformation and then to the other gauche. Yeah?
Wouldn't you still have to go up that big hill coming back?
Well, if you wanted to go back from here to there, you would simply go back the other way. In other words, probably not very often do we traverse this high energy barrier because it's so simple. It's so much simpler to go the other way.
That's why it bounces back and forth.
That's why you saw it bouncing back and forth in the program. Yeah.
So is it why on E2, the highest energy conformation, the difference in energy is greater, I think, in that hill, the middle hill, than the second hill?
Right. Yes, exactly. If you compare going over this barrier versus going over that barrier, or similarly going over this barrier versus that barrier, this barrier is a lot lower. And we're going to see in reactions that speed of reaction depends on how high that energy barrier is. This is called transition state theory. President Eyring's dad was a chemist who contributed a whole lot to this idea early on in the 20th century, and the idea that how high an energy barrier is determines how fast the reaction goes is fundamental to chemistry. And so yes, it's much faster to go than it is to make the big hike. All right. Yes?
Do you keep some of the energy when going from like G2 to A to go back up A?
Do you keep some of the energy when going from here to go up this? I think if we're thinking in terms of like off-roading in a vehicle, and then that sort of makes sense. I don't exactly know at the molecular level what that looks like. But yeah, do you have enough kinetic energy that you can get back up? And that would depend on the temperature. So my guess is that at room temperature, you can easily go back and forward from anti to Gauche 1 and from anti to Gauche 2. My guess is it's quite a bit more difficult. I think this barrier is maybe 10 kilocalories per mole high. I mean, depending on what your text says. That's probably high enough that it's not happening a lot, at least not at room temperature. All right. Okay. So yeah, that's why if we go from, yoink, no, the bath temperature is too low. Yeah, go from this conformation, it's probably, if you noticed, actually the molecule resisted going through that anti-conformation. Did you see how it would rather actually move around in space than have those methyl groups slip past each other? Okay. So that's conformations around bonds when there's only two things. Go ahead.
And the methyl groups don't want to be next to each other just because, like, steric strain and just kind of.
Right, just because steric strain. We're not using hyperconjugation here because we use that to describe why staggered conformations are better than eclipsed. But the only difference between these staggered conformations is the sterics. Yeah.
The study guide mentioned that you measure the steric influence by A value.
Right.
Is it just strictly the size of the?
Right. So how do you? The question is about how do you rank the size of various groups, because you can see we could make this situation more complicated. Why would we do that? But we could make this situation much more complicated if we changed what one of the substituents was. So as an example, let's change one of them in the back to an OH group. And of course now, why did we do this? Because we can. I'm losing track of where my OH group. Whoa, it went on the wrong carbon. Yeah. We're totally making stuff up. OH and then OH, right? Okay, now it doesn't make sense to call any of them anti or gauche because it's like gauche to what, anti to what. So we'll call this one staggered 1, staggered 2, and staggered 3, and back to staggered 1. So let's just briefly compare staggered conformations and see whether we can make some conclusions. And I will just tell you, and you could probably guess this just by sort of drawing out the groups. The OH group is smaller than the methyl group. We do have a measure of size in organic chemistry that's called an A value. Its origin, we're not quite ready to talk about yet. It's given in kilocalories per mole because it's derived from an equilibrium experiment. For the OH group as a substituent, the number is 1, and for the methyl group, it's like 1.7. So this tells you how much worse it is to be near a methyl group than to be near an OH group, roughly. And the numbers are not important, the trend sort of is. So OH is smaller than CH3. So with that in mind, let's see if we can rank the S1, S2, and S3 conformations. All right, and to do this, it's useful to think about what gauche interactions we have, or what times non-hydrogen things are gauche to each other. So in S1, we have a methyl group that's gauche to an OH group. In staggered conformation 2, we have a methyl group in the front that is gauche to an OH group and to another methyl group in the back. Do you see we're gauche to both of those here? And then staggered 3, the methyl group in the front is gauche only to another methyl group. All right, based on what you know about the relative size of these groups, can you rank these staggered conformations in order of decreasing badness? So start with the worst and go from there. What have you got? S2 is the worst. Why? It's got the most gauche stuff. The mostest stuff is gauche to the other stuff. I don't know. Highest energy.
Okay.
Yep. So highest energy is S2. Then what? S3 because methyl is bigger than OH, so a methyl-methyl gauche interaction is worse than a methyl hydroxy gauche interaction. All right, so we're not going to put numbers on this, but just the relative order is useful to be able to do. And I've often asked questions on exams, which of these is the lowest energy conformation of molecule A, or whatever it is, right? I'll give you another secret. This isn't going to make sense now, but it will a little bit later when we get into chapter 5. Notice how in this molecule there are only 3 staggered conformations. There's no, about a single bond, about a carbon-carbon bond, about a bond between sp3 hybridized carbons, there's only 3 possible staggered conformations. So if I ask a question where I say, which of these is the lowest energy conformation, and I give you 6 or 9 staggered conformations, what do you automatically know? Only 3 of them are even going to be the right molecule. Okay, so I am evil. One of the things I've done to generate bogus answers in the past is to change the molecule such that it's not even the same molecule anymore. It doesn't make a lot of sense here, but moving the OH group to the wrong carbon as an example. And so you have to be careful. I don't think I've necessarily disclosed this before, but I'm feeling generous today. If you just memorize the idea, okay, the most stable one is where the most biggest stuff is farthest apart, then you could easily, in a hurry, select this answer as the best answer, but that's not even the right molecule. And if you're in a hurry, you're going to do that, then you're going to come to my office and say, why isn't this the right answer? And I will say kindly, because if you look, that's not even the right molecule. And then you're going to go, oh, I see that now. Why didn't I see that before? So consider yourselves duly warned. All right? We'll learn later on about how to draw Newman projections and make sure you're getting the right molecule, but that's going to require us to get into Chapter 5 in stereochemistry. Okay. Any other questions you want to ask about that? Yeah? For alkenes, yeah. Does this mean, going back to alkenes from the previous lecture, we talked about not rotating around. But yeah, if you're going to form an alkene, the most stable way to do that would be such that the two groups are trans to each other. The two biggest things are trans to each other. That may or may not be possible depending upon the structure of the starting material, but we got to get through 5, 6, 7, and 8 before we're ready to consider that. Okay? Yes?
Just to clarify, the hydrogens are still gauche, but we just ignore them.
That's right. You can still say that any two groups are gauche to each other, but we're ignoring them in the sense that we're basically making the assumption that gaucheness to a hydrogen is about the same whether or not it's a methyl group or an OH group. I suppose we could have included those in the analysis. I don't think it would have changed our conclusions because why? I don't know. Yeah. That's unsatisfying, isn't it? I mean, if we wanted to, we could enumerate all of the other gauche interactions. The rest of them would be between non-hydrogen groups and hydrogen. And I think we're counting on the biggest differences being in the differences between the non-hydrogen things. Yeah. All right. So now we need to deal with rings. All right. And so this is aversion therapy in a certain way, in the sense that if you feared rings, we're going to learn to fear them less. The other day I was on a walk in our neighborhood with Amber, and we walked past the front yard of a friend. They weren't out in the yard, but a snake was out in the yard, and I do not like snakes. I'm not prepared to admit that they are real. For some reason, it's this irrational fear, but instead of running and screaming, I paused and I looked at the snake as it slithered away from me. Amber's like, Josh, go touch it. Touch it. I'm like, no. So I looked at the snake. Today we're going to look at the rings and hopefully decrease your fear of them. Okay. So when we deal with rings, or another way to say this is cycloalkanes, we're dealing with an issue called ring strain, okay? And ring strain comes from a couple of things. It comes from bond angle strain, and it also comes from what your book calls torsional strain. Torsional strain is what we've just talked about above. This is steric hindrance due to gauche clashes, like what we dealt with up here. The fact that this conformation S2 is higher in energy than S3, your text will call that torsional strain. I call it steric hindrance. Doesn't matter. So when you take something like propane in which all the bonds are free to rotate, and in which the bond angles can very easily be at their idealized 109.5 values. And then you constrain it to be in a triangle by connecting carbons 1 and 3. Suddenly, geometry becomes an issue, because what in a triangle, and I haven't drawn this nicely enough, it should be an equilateral triangle. It has to be, because the three carbons are all equivalent. In an equilateral triangle, what do the angles have to be? 60. There's a formula for that. I don't remember what it is. You could tell me, but I will forget it, so don't bother. But that bond angle is tighter than it's supposed to be. So that would mean an sp3 carbon needs to distort its geometry to push bonds that would rather be further apart because of electron-electron repulsion to be closer together. All right? That's called angle strain. Now, it's not enough to prevent formation of the ring. There's a lot of cyclopropane rings in organic chemistry. But there is, if you compare energies of the acyclic molecule versus the cyclic one, there is some ring strain associated with that. So we've talked about angle strain, which is difference in the angle versus the idealized value for an sp3 carbon. We can also talk about torsional strain in this molecule if we, say, look down one of these carbon-carbon bonds. If we did that, what we would see, here's one of the carbons of the cyclopropane ring, the other carbons in the back, we would see that the ring forces all of these things to be eclipsed with each other. And there's not really a good way. In fact, you can't do anything to relieve that problem. And so that's unfavorable. Okay? Now, when we get to, and this is for cyclopropane, and the high torsional strain you get just because 3 points define a plane, and there's no other way to make the shape of this molecule. When you get to the next one, cyclobutane, if we draw this sort of looking down from above, we would say that if this were a perfect square, then what would the bond angles have to be? Have to be 90. That's not as far away from 109.5, so there's a little less angle strain than in cyclopropane. Though, again, if we did this, if we looked down one of these carbon bonds, if the square were completely flat, we would see, I guess we can do a double Newman projection like this. We would see all the carbon-hydrogen bonds in the front eclipsed with carbon-hydrogen bonds in the back. And that would be a lot of torsional strain if the molecule were flat. Now, because we've got 4 different atoms in this ring, we're a little bit freer to rotate. And so what will happen is that the molecule will distort its structure. We're going to look at this from the side. Instead of being perfectly flat like this, the molecule will relax, and it's called puckering, and it will adopt a conformation that looks a little bit more like this, where the bond angles are no longer constrained to be 90 degrees, and where the carbon-hydrogen bonds are no longer that eclipsed with each other. So this would be the puckered conformation of cyclobutane, and it allows you to relieve some ring strain. Don't know why they call it puckering, but that's kind of what we're stuck with. I'm looking for cyclobutane. I'm not sure they've got it. Cyclobutane, there we go. So, do you see how that's not a perfect square? Do you see how one of those atoms is out of the plane, distorted out of the plane? Apple Pencil battery is low. Thank you for warning us. Here's us looking at it from the side. That's sort of like what I drew. If we look down any one of these carbon bonds, do you see that it's no longer perfectly eclipsed? So what I mean is by adjusting from planarity, these rings can actually relieve some angle strain and some torsional strain. There's not a good way for us to measure these angles using this program, but if you did, you would see that they are wider than 90 degrees. So by relaxing a little bit, it's able to relieve some of the torsional strain. So the same is true, perhaps even more true. So overall, the puckered conformation has less angle and torsional strain than the flat conformation. So in general, remember that rings composed of sp3 carbons are generally not flat. Rings other than cyclopropane, rings composed of sp3 carbons are generally not flat. They adjust their shape. The same is true for the 5-membered ring. So this molecule distorts itself to be kind of like the puckered conformation. You have 3 atoms that are in a plane, and then one that's above and the other that's below the plane. You sort of have what some chemists creatively call an envelope conformation, as though this were the flap that you're about to fold down. There are many possible envelope conformations. There are many possible envelope conformations for a 5-membered ring, and they're all pretty similar in energy. We won't worry about them too much. Also notice that the 5-membered ring, even if it were flat, should have less ring strain than the 4-membered ring, because the bond angle here can get even closer to 109. And I don't know what the bond angle is. I always get to this point and I remember that I forget what it is for the pentagon, and then I decide I don't care to learn it and I move on with my life. Here is cyclopentane, if they have it for us. Yep. So looking at that, you can see in the front are the 3 carbons that are basically in the same plane. Hold on. And then the one in, oh, you can't even see. It's not even going to make sense. Basically, you have 3 of them at any given time that are in one plane. You have one that's above and one that's below. And then it subtly shifts who's who. And it's called, I forget what the term is for that kind of thing, ring wobble or something or other. 5-membered rings are common in OChem. You see them all over the place. The one that you're going to get the biggest experience with is the 6-membered ring. And it adopts a conformation that looks like this. And for various reasons, we call that conformation a chair. So your task is to get good at drawing a chair. And we're going to talk about that conformation in greater detail next time before we move on to Chapter 5. All right. Have a good day. I'll see you on Friday.